All right, so let's talk about the graded junction HBT. And this is in the context of we're just discussing the abrupt junction, where you have this spike or this barrier in the for the electrons, and the only gain we got in beta was not the full gap we had hoped for, but the delta EV was the only term that was showing up in the improvement of the gain. So let's look at a graded junction and see what we can do there. So the idea here is to start from a material where we can convert this abrupt junction into something that gets rid of the spike. So here it looks a little bit different, but this is just given a certain bias condition, etc. Let's look at it this way. We can write down the conduction band edge as some E0 and the difference in the electron affinity along X and the built-in potential. And we can write down the valence band as a difference between the conduction band and the gap. Okay? So we can obtain these values spatially. Okay, we've built in this built-in potential, and we learn how to calculate it. And together with the built-in potential and the difference in the electron affinity, we can now obtain the overall structure. Now, band edge diagram. So what if we could grade this electron affinity and grade the band gap? Okay? So what if we not had an abrupt junction but a graded junction? If that's the case, we can actually tune away this spike in the conduction band for the electrons, and we can end up with a junction that looks like sketched here. Okay, so you have a graded transition for the material, and this would be here on the chi, the electron affinity, across the junction, and you've gotten rid of the spike, okay? And what you see now looks like a really smooth band edge diagram, and basically you've increased here the difference of the band gap quite a bit here in the valence band. So you transitioned the difference in the band gap into a region where you don't care, or you actually like it to be, right, bigger. Because what you really want is you want to block holes flowing in this way, or more accurately, this way, right? So you increase the gap in the right direction where you want to block carrier flow, and you make the transition for electrons smoother. All right. So let's write down the expressions. We don't have a heterojunction. We can use the normal drift diffusion expressions we've had before. Again, everything works the same. We can write down a differential equation for the electrons and see that they're linear dropping. We know how to calculate the boundary conditions. All of that stuff just transfers directly as if we had the normal BJT. Okay, so same expression, but we've modified NIB here. Okay, so in this expression here, there's no more delta EC that is blocking some current. We have the very same expression again for the holes. Again, nothing changed. The only difference here is that we have now a different NIE squared in the expression. We can build the ratio, just like as what we've done before. We can write down this NI for each of the different materials as a function of gap. And then we see immediately the beta has the difference in the band gap built into an enhancement of beta. Okay, so that is what we wanted. And this is called a graded junction HBT. All right. So if that's the case, That's what we want to build. Let's step back a little bit. What have we achieved with doing this, okay? So again, we have now a heterostructure that if you squint your eyes a little bit, it looks like a BJT. The band profiles look virtually identical. And if you don't squint so much, then you realize that the gap here is larger than the gap here, okay? So you go from 1.8 to 1.42. So that's a pretty dramatic change in band gap. So what does that do? So let's look again at the desired forward current of the electrons, the minority carriers being injected from the emitter in forward bias into the junction, okay? We want to have that current be high. And the control current that we need to control the overall current and the forward bias junction that we pay for is this JP. We'd like to have that as small as possible, right? So again, I had argued that you can increase NI and decrease EG. That's the same slide as what I showed in an earlier section. And you want to reduce the whole current, okay? So this is all good, right? You're making a much bigger rejection or making it much harder for whole current to flow, and you keep it easy enough for the electrons to flow forward. But what does that buy you? Okay, here's the argument: emitter should be greater than the in the emitter and than the base. Okay, now let's figure out what that buys you. Okay, so we're going from 1.8 eV to 1.42 eV as a total band gap difference. So that's 380 millielectron volt. Now, compare that to the thermal budget of KT at room temperature, that's roughly 25 millielectron volt. Okay? Let's see what that does to this gain. Okay, we're going to calculate delta EG over KT. So we have e to the 380 over 25. That is e to the 15.5. That is 4 million. 4 times 10 to the 6. That's a pretty large increase. It's a huge increase. Remember, we played around with changing factors of doping by factors of 10. So we can up and down the transistor beta with factors of 10. Now we're talking about factor of 1 million. That's a dramatic game changer. Now you can turn on your idea factory. You can have opportunities for alternative thinking on how to optimize your transistor, because you have this tremendous knob which allows you to crank up beta, and maybe you can trade in some things that you wouldn't want to do before. Okay? All right, so let's look at these opportunities for alternative thinking. All right, in the past, we wanted to have a thin base for speed, okay? We wanted to have very fast transit times so we can crank up the operation frequency under AC. We also wanted to have a thinner base because here, if we make this small, we can crank up beta, right? But if we made it too small, we saw that in the early voltage and at punch through, right? Remember, early voltage performs like this, and this modulation, this slope here, was the early voltage, the overall distance here, and that was the base width modulation, okay? You can even make the base under high current flow could become so small that you had punch through, that you lose the whole junction, okay? So making the base smaller was cranking up beta, but it had detrimental effects in the other if you did it too aggressively. Okay, we also talked about increasing the base doping. So that was increasing this and therefore ramping up beta. It would have increased the early voltage. It would have made the curve flatter, reduced the modulation, but it would have caused a reduction in beta, and we were fighting for every little bit of beta we could get. Now, all of this is more possible. So we just got a factor of 1,000,000 out here. Whether we can realize it, that's a different story. But we're no longer talking of factors 2 or 3, trade up and trade down. So now, what you can do is you can trade these different design features. Okay, you can talk about a heavily doped base. Yeah, so you go up by a factor of 10 in base doping. And yes, that will reduce your beta by 10, but it'll make the transistor much better by making it flatter. It'll eliminate the modulation of your base. It'll also, remember we had the current crowding issue, the corner effects. It'll reduce the resistance in your base. So it's overall a better design. It also prevents the punch through, okay? So you can crank up the base doping. You can also lower the junction capacitance, the base-emitter junction capacitor, if you change your doping in the emitter. So you can reduce the doping in the emitter a little bit, and if you do that, you increase your depletion regions, right? And if you do that, you place the charges further apart, you reduce your capacitance, okay? So you can reduce the base-emitter junction capacitance. So you have opportunities for improvement. And what people are using now is something called an inverted base doping. So it used to be that you want to have NB less than NE, right? In the last lectures, we had these 3 bars, right? This was E, base, and C for the doping levels, right? Now you can flip it. So that's the opportunity that this heterostructure affords. Okay, so we talked about a graded junction. Seems like we've gotten all we want, but there's a little bit more you can tease out, and that's going to be the graded base HBT. And we'll talk about that in the next section.